This video covers essential best practices for optimizing the performance of C++ applications. It explores techniques for writing efficient code, optimizing CPU and memory usage, and selecting the right data structures and algorithms for performance-critical applications. By following these best practices, developers can enhance their C++ programs, reduce resource usage, and achieve faster execution times. Introduction to C++ Performance Optimization. In this video, we'll focus on improving the performance of C++ programs. This is especially important for applications that require real-time processing or run on systems with limited resources, such as embedded devices. Efficient code helps reduce resource consumption and ensures smoother user experiences. Tip 1. Choose the right data structures. The choice of data structure plays a significant role in performance. For example, std::unordered map provides constant time complexity for lookups, while std::map maintains order but has logarithmic time complexity. Understanding the strengths and weaknesses of each data structure will help you write more efficient programs. Tip 2. Minimize memory allocation and deallocation. Allocating and deallocating memory repeatedly can slow down your program, especially when done in performance-critical sections. Memory pools or custom allocators allow you to manage memory in bulk, reducing the overhead caused by frequent allocations. Always try to reuse memory whenever possible. Tip 3. Optimize loops and iterations. Loops are often the most critical part of your program in terms of performance. Minimizing the operations inside loops and unrolling them when possible can help reduce overhead. Also, using iterators with containers like std::vector allows you to traverse elements efficiently, avoiding unnecessary function calls. Tip 4. Prefer pass-by reference for large objects. Copying large objects in C++ can be very expensive, especially for complex types like large containers or classes. By passing objects by reference, or pointer, you avoid creating a copy. Using const references ensures that the object is not modified, making your code more efficient and clear. Tip 5. Use Move Semantics and Rvalue references. In modern C++, Move semantics allow you to transfer resources from one object to another without the cost of copying. By implementing move constructors and move assignment operators, you can make your code more efficient, especially when working with larger objects or containers. Tip 6. Avoid unnecessary virtual function calls. Virtual function calls, while essential for polymorphism, add overhead due to dynamic dispatch. In performance-critical areas, it's best to minimize virtual calls. Instead, you can use alternatives like templates or std::function for polymorphism to avoid the overhead associated with virtual calls. Tip 7. Profile and measure performance. Optimization should always be data-driven. Instead of assuming where bottlenecks are, use profiling tools like GProf, Valgrind, and Perf to analyze performance. Profiling will identify the real hotspots in your code, helping you focus your optimization efforts where they'll have the most impact. Tip 8. Use compiler optimizations. Compilers like GCC and Clang offer optimization flags that can significantly improve performance. The O2 flag enables general optimizations, while O3 applies more aggressive optimizations. However, it's important to test the performance before and after applying these optimizations to ensure they have the desired effect. Tip 9. Avoid expensive exceptions in performance-critical code. Exception handling in C++ can be costly, especially when used in performance-critical code paths. It's best to avoid throwing and catching exceptions in frequently executed functions. Instead, consider using error codes or other mechanisms for handling errors where performance is crucial. Tip 10. Minimize use of recursion in performance-critical code. While recursion is a powerful tool, It can be inefficient due to the function call overhead and potential for stack overflow. In performance-critical code, try to rewrite recursive algorithms iteratively, or if deep recursion is necessary, use a stack-based approach to avoid excessive memory usage.